Okay, I think we can start. So this is not directly related to systemic risk, but there is quite a lot of interest at the moment in the subject of backtesting, particularly backtesting the expected shortfall risk measure, whether that's possible, and there's quite a lot of interest in the elicitability theme, what that means, and if it's relevant for backtesting at all. I got interested in this because quite a long time ago I made one proposal for a backtest for expected shortfall in the context of a paper I wrote with Rüdiger Frey on sort of dynamic models for tail risk, and so that was one entry into this for me. And okay, so I think probably I'll just get straight into it and explain a little bit more as we go on. This is what I plan to do. So I'll give the context, backtesting estimates of risk measures for the trading book, sketch the problem. I'll talk about backtesting value at risk to begin with, so we have so that we see how things work for in the easy case of value at risk. So there'll be theory, simple binomial tests, related tests, and I'll also mention at various points some other papers which have influenced me in preparing this talk, things that I've found interesting. So the consistency idea I learned from Mark Davis, and he can tell me if I've interpreted it correctly after I present it. And then the other paper that's quite prominent here is a recent paper by Acerbi and Seikei on backtesting expected shortfall. So in section 3 I'll get into that topic, and I'll explain how this Acerbi-Seikei test works and whether it's a good idea or not. And then in the fourth part, backtesting using elicitability, and then finally I'll try and draw some conclusions on all of this. So to begin with the introduction, backtesting. So this is all motivated by proposed changes to the risk measure for the trading book. There's some suggestion in the fundamental review of the trading book that we should switch to the expected shortfall risk measure. After years of academic lobbying that value at risk is a poor risk measure for various reasons, it's incoherent, it does not tell you about risk beyond the value at risk, beyond a certain percentile. The idea has been sown in regulators' minds that it would be a good idea to look at expected shortfall. So one of the questions in this presentation is, can you backtest estimates of expected shortfall? So in the trading book contains assets that are available to trade. We contrast it with the banking book, which contains the more traditional banking type assets like loans, which are held to maturity. So trading book assets, you're supposed to be able to give them a fair value at any point in time. You might be able to look up their values, that is to mark them to market, or you might have to mark them to some model, to a valuation model whose inputs are things that you can observe in a market. But at any point in time, you should be able to value the trading book using fair value principles. So it contains market type instruments, may contain derivatives, lots of different fixed income instruments. We usually, or at least the way that the regulation is developed, the trading book is usually identified with market risk and the banking book is identified with credit risk. But of course, there is plenty of credit risk in the trading book, and there's also market risk in the banking book. So this is a crude dichotomy to split things this way. The Basel rules say that if you can seek approval for an internal VAR model for the trading book, an internal value at risk model, and the idea is that you develop a model for the P&L distribution of your trading book portfolio over a particular period of time. The canonical length of time is a 2-week period, a 10 trading day period, and from this model you compute the value at risk estimate. But you could equally compute an expected shortfall estimate if you have developed a model. And the uses of these risk measure estimates, they're used both internally and externally. Externally, regulatory capital requirements are related to these risk measure estimates, well, the VAR estimate at this point in time, and they may be used for internal limit setting. So I'm not going to discuss the philosophy of whether this is a good idea or at all. I'm not going to go into the problem of is it a good idea to relate capital requirements to these kinds of measures for the trading book. Instead, I'm going to tackle the problem of, okay, this is what we've been told to do. How do we do it, and how do we backtest the numbers? So it's a largely econometric or statistical talk rather than the philosophy of whether this is a good idea. But one thing that it's quite important to realize is that this problem, it changes all the time in a very dynamic way. So it makes conventional statistics very difficult. So just the only reason I go through this slide is to emphasize the time dependence of what goes on. The notation is taken from the way that, from my textbook, from the way that we develop the models of trading book risk in my textbook with Rüdiger Frey and Paul Embrechts. It occurs to me that it is on. Okay. Okay, so at time t, there's a set of risk factors. I call them Z. This is everything that can be looked up. It's prices and rates, exchange rates, interest rates for different maturities, even volatility parameters that can be inferred from prices. So ZT contains what people call risk factors, and this act of valuing the trading book at a particular point in time could be captured in a formula. So formula 1 there says that the trading book value is some function at this point in time, which depends on these risk factors, and also explicitly on time, because there will be the things in the trading book whose value depends on time to maturity or time to expiry, etc. But this function ft is specific to this point in time. It's the portfolio mapping at this particular point in time. And if we do the same exercise tomorrow, it's a different ft because the trading book has changed. Certain positions have been liquidated, other new positions have come into the trading book. So it's specific to this point in time. So mark to market and mark to model are all embodied in this formula 1. I mean, certain things that are in the trading book can be marked to market, that is, they are part of the vector ZT. Other things are marked to model, that is, they are valued using a model which references the vector ZT. So ZT is known at time t, VT is known at time t, and the problem in measuring risk is looking one time period forward. So let's say that's 2 weeks, or 1 week, or 1 day. I don't really care how long it is in this particular talk, but it's a short time interval, and we'll call it t to t plus 1. And the value of the trading book is going to go up or down, but let's focus on the loss. So the loss in the trading book is just given by the change in value multiplied by -1, and it is going to be some function of the way that these risk factors change. That's the key thing. So at the end of, so the value at time t plus 1 for this portfolio, assuming it, I should say something very clearly. So we assume the positions are held over the period t plus 1, and we ignore any income that may come in this period. So Vt plus 1 is given by this, Vt is given by this, and of course the whole stochastic nature of this comes through the way that these risk factors change. So xt plus 1 has been introduced as the difference of the two vectors of risk factors, which will be of high dimension. So the loss is some other function, again indexed by time, of the way that these risk factors change. And in our textbook we call this a loss operator. So the important thing is that this changes all the time. Now ideally the bank, I say ideally because if you really want to compute an estimate for the next time period, you would be advised to use all the information you have about risk factors in the recent past. So ideally, the bank estimates the conditional loss distribution, the distribution of losses. So that's this function of the way that risk factors change, given information available at time t. I'll be a little bit informal about what this information is, but typically it would be the information in past risk factor values or past increments or changes in these risk factor values. I say ideally because many of the methods that are actually used in the trading book, for example, the method they call historical simulation, implicitly and without really acknowledging it, they take a more unconditional or a stationary view. So they basically attempt to estimate the distribution of this, where x is simply a vector that has an assumed long-run stationary distribution for these risk factor changes. So implicitly, many of the models do this, but ideally, we should look at the conditional distribution. So I'll assume that what we do is, what the bank does is it forms an estimate. So I'll call the estimate f hat, and it is particularly concerned, or should be particularly concerned if it's doing a good job, to derive an estimate that is good in the tail of this loss distribution. And I will write var alpha t and es alpha t for the alpha quantile and the alpha expected shortfall of the true but unknown underlying conditional loss distribution at that point in time, and I'll write var hat and es hat for quantities that are for estimates that are derived from the model. So they are computed from the model f hat. This model may be parametric, it may be fully parameterized in some form, or it may be non-parametric. It may be estimated through basically some empirical distribution function technique. In addition to the basic form of historical simulation, there are variants which attempt to actually estimate this conditional loss distribution. So I assume that's what happens. Just a reminder of the two risk measures, which is probably not necessary for this audience. If FL is a generic loss distribution function, and my alphas will be large alphas, so 95%, 97.5%. Var alpha is the alpha quantile of the distribution function, i.e. the inverse at alpha. Es alpha is the integral over the quantile for quantile levels from alpha to 1, divided by 1 minus alpha, or as is well known, if we just assume that we have a continuous distribution, it's the expected loss given the loss exceeds the var. And we will just assume, for simplicity, that we're always dealing with continuous loss distributions, so expected shortfall is computed in this way. Okay, now what's the backtesting problem? What can be said about the problem? So we compute these estimates at time t for whatever loss operator we're dealing with at that point in time, which is determined both by the composition of the trading book and by the values of all these risk factors at time t. We compute these things and we compare them with what actually happens at time t plus 1. So one step further on, we can make the comparison. We can see what happens. How does the loss relate to the var we estimated one step back? Now, what's interesting about this experiment is it's a complete one-off and it's unrepeatable. So at time t, we make this comparison, but at time t plus 1, the next time we make a comparison, this loss operator function will change, and it will change because the portfolio changes and also because it references the values at time t, which will change, and the conditional distribution of risk factor changes will also change. So the experiment happens once. And what I found, an interesting idea I found in Mark's paper, just a discussion of whether it's meaningful at all to test the idea that this true distribution takes a certain form. The idea of a true distribution, I agree it's very abstract. We're only ever going to see one observation from this distribution, and then we're going to move on. And so it's very difficult to test a hypothesis specifically about this distribution. To test the hypothesis that this distribution takes a particular specified form is almost meaningless. Mark talks about being unfalsifiable. We can't say whether our hypothesis is true or not, and therefore meaningless. However, in this talk, I'm going to stick with the idea that there is this true underlying model, even if we only see one number from it. But over time, we're going to have a look to see whether the models we use tend to over or underestimate the quantities in which we are interested. So we can never reject a hypothesized model at a particular time point, but if we collect evidence over time, we can see that whether we have a tendency to work with models that are deficient in some general way. They're deficient in that they tend to underestimate quantiles or underestimate expected shortfalls. Okay. Another idea that I'll just mention, because Ram is in the audience and is also relevant, but I won't go into in a great deal of detail. There is the issue of the robustness of the estimators that we use to estimate these quantities. So in particular, estimators of expected shortfall lack robustness. They tend to lack robustness. If you add points to the data set, if you remove points to the data set, they move around a lot. That's the crude intuition. They're unstable when the data are perturbed. So robustness is not a property, or lack of robustness is not a property of expected shortfall per se. It's a property of an estimation procedure for a risk measure. So, or to put it the other way, robustness is a property of an estimation procedure for a parameter or a statistic of a distribution, or a law invariant risk measure, which is a statistic of a distribution. But it's not a property of a risk measure. So even with value at risk, we could choose estimation procedures which lack robustness. Although the very simple, common way of estimating a value at risk, which is through a sample percentile, is a robust procedure for estimating value at risk.
But I don't get this distinction, because if you look at the theory of statistics, I mean, a statistic in the theoretical sense is a map from distributions to numbers. So
yes,
it is a risk measure. It's the same thing. And in fact, a lot of this theory of coherent risk measures can be read off from Huber's book on, you know.
Yeah. Okay. A risk measure.
Statisticians call it a statistic.
Mm-hmm.
But what statistician calls a statistic is really a map from distributions to numbers.
Yeah. Okay. It's yes. Yeah. So yes. So yes. Or a particular risk measure, parameter or a statistic or a risk measure. I agree, we're talking about the same thing. That will become more explicit when we look at the elicitability, where you see that functionals of distributions are risk measures. They are the same thing, with a slightly different formal approach usually, but I agree. So no disagreement at that point. Okay, so backtesting value at risk is fairly straightforward. Okay, so let's talk about violations first. So var alpha t is the true underlying alpha percentile of the conditional loss distribution. And if the loss exceeds it, this is a var exception or a var violation. I say theoretical because later we'll put hats on the estimators and look at the actual violations. And this event has this indicator, so IT plus 1 is an indicator that it happens, 0, 1. And we have the property that because this is the quantile of this distribution, that the expected value of the indicator, given information to time t, or the conditional probability of a violation, is 1 minus alpha. Okay. Now, what is quite nice is that when you have this property, it may be shown that a process adapted to a filtration and satisfying the quantity a process of trials of this form, and satisfying the property that the expected value given the past is always the same thing. This is a Bernoulli trials process. This is a process of independent, identically distributed random variables, which is actually quite remarkable. So it doesn't really matter what the underlying model is. If the conditional expectations are always the same for these events, then you have a Bernoulli trials process. And so the implications are several-fold. So these are independent Bernoulli events. So if you sum them up, you have binomial distributions. So if we sum up these indicators, we have binomial distributions. If we look at the spacings between the exceptions, we have geometric random variables, independent geometric random variables. So most of the tests of value at risk are based on this observation that you get a Bernoulli-Trials process when you look at these violations. This is an example. So at several points in this talk, to make things more concrete, I take the example of the Gauge process, not because that represents in any sense the trading book, but because it has some of the features of financial prices and is a nice model to talk about the theory of backtesting. So that's a realization of length 2000 from a Gauge process, and every red dot represents a theoretical VAR violation. It happens when what the actual realized value exceeds in this case, the 97.5 percentile of the conditional distribution of the return for the next time period. So you get these violations, and they should form a Bernoulli, so whether you have a violation or not, that should form a Bernoulli-Trials process, or will form a Bernoulli-Trials process. Those are independent, identically distributed Bernoulli events. And in this case, we get 59, so the actual level is 97.5, so there are 59 of them in this particular realization. And the red dots, if you like, are a realization of this Bernoulli-Trials process. So that's these are the points at which they occur. These are the spacings. It's just a quantile plot against geometric. And it's not that this hasn't been cherry-picked as the greatest quantile plot, but these spacings should be geometric. Okay, so the next idea I wanted to bring in was the idea of well, it's called various things. In Mark's paper, it's called a calibration function, in Mark's paper on backtesting. In other literature, it's called a signature. So that's what this slide is about. But first, one other piece of language. There's a paper by Christofferson in 1998. If you simply test the binomial behavior of the number of violations, that is called a test of unconditional coverage. If you simply check that the number of exceptions is about right, that is a test of so-called unconditional coverage. If you also check the hypothesis of independence for these violations, that is a test of conditional coverage. We'll come back to that in a second. Now this identity here 4, this property here 4, this tells you how to create what's called a calibration function. So the property 4 can be expressed in terms of a calibration function. It's also known as a signature in some of the elicitability papers, but we can write the expected value of some function of the value at risk and the loss given ft equals 0. And the particular choice of the function here is this one here. Alpha is a parameter of it. It's a function of the quantile estimate and of the loss. So the indicator minus 1 minus alpha. And what is remarkable is that the process of these things, so the calibration function evaluated at the true conditional quantile, and the loss forms a process of mean zero IID random variables. And so that regardless basically of the underlying model, you have a process of mean zero IID variables. And this is actually what makes VAR backtesting very nice. When we look at expected shortfall, we're never able to make quite such a strong statement again. Okay, so let's come to the actual tests that you could perform. So in practice, what do? You estimate VAR, but using the model at time t. So you have a series of estimates of VAR. They will have a t on them. And you're interested in the hypothesis that you, in general, correctly estimate VAR. So the exceedance probability tends to be 1 minus alpha, against the alternative that you have the tendency to underestimate VAR. So the null here is completely equivalent to the hypothesis that VAR is correctly estimated at all time points. Okay, if this is true, VAR is correctly estimated at all time points, whereas the alternative is saying that there is systematic underestimation. So greater or equal to 0 at all time points, and let's assume that at some time points it's actually greater than. So under H0, this is all we're really saying under H0 is that the probability that you exceed the estimate is 1 minus alpha. So therefore, the indicators for violations of your estimates should form a Bernoulli trials process. They should be independent, identically distributed Bernoulli events. Actually, this should be event probability 1 minus alpha because it's the probability of exceedance. Yeah, there's a question, yeah.
One question. Why is H1 not a two-tailed test but a one-tailed?
It could be. There's no reason why you couldn't do a two-sided test. You might be concerned about overestimation as well. But let's assume that that you have to convince an external person that you're not willfully underestimating the risks. So let us focus on the more pessimistic one-sided test. But that's quite true. So that's how the hypothesis would be formulated. Then there's all kinds of things you can do. You have a set of numbers, zeros and ones, the realized values for these indicators. If you sum them up, this should be a realization from a binomial distribution, and there's various ways that you can test for binomial behavior. You can do likelihood ratio tests in Christopherson score statistics, or you can just compare the number with a binomial distribution. But the other thing that you need to test is the independence. You need to test the so-called conditional coverage. And again, there's quite a lot of literature. Back in this paper by Christopherson, I think he was the first person to propose some sort of test for the independence. So he tested independence against an alternative that in fact these violation indicators had a first order Markovian behavior. And in Mark's paper I see something similar. I don't know, I think it's slightly different, but again, testing for Markovian, testing against the alternative of a Markovian dependency. Another paper suggests a test based on the Weibull distribution. Because violations are rare events, the discrete time Bernoulli trials process, you could think of it or approximate it through a Poisson process, that violations occur essentially as Poisson events, and these geometric spacings you could approximate as exponential spacings. And so Christopherson and Pelletier, they suggest basically testing the null hypothesis of exponential spacings against an alternative of Weibull spacings. The exponential says that the hazard of a violation is always equal. The Weibull says that that hazard can either increase or decrease, but the interesting alternative is that there is a decreasing hazard. So immediately after a violation, the risk of another one is higher, and then it tails off. So there's all kinds of tests that can be carried out to check whether you have a Bernoulli trials process.
There must be hundreds of these tests in the computer science literature aimed at testing the random number generators of really random numbers.
Probably, and this is probably the tip of the iceberg. But
yeah, I don't know where to find these things. Somebody said Donald Knuth is the guy for this, but I haven't looked. I don't know if anyone else knows. Well,
so, okay, so just a word about consistency. Having introduced this idea of the calibration function, that's this function that gives us this identity. I just note that in Mark's paper, this calibration function is used as the basis of another form of model checking. These things, as I've remarked, they are basically IID, Bernoulli variables. If you sum them up and normalize them in some way, the limit as m goes to infinity is going to go to 0. So you may actually just take the sequence Bm to be the sequence m, and then by the strong law of large numbers, this is true. But you can show it for sequences which don't grow quite as fast as the sequence Bm equals m. And so I see in Mark's paper, he introduces the idea of consistency. So in the language of that paper, what you would say is that if this happens, var is consistent with respect to the calibration function h alpha, whatever sequence you use, bm, and this is going to be true, in fact, for all models in which if we always assume that these conditional loss distributions are continuous. So this property is consistency of a particular risk measure with respect to a calibration function, a sequence of a strictly increasing sequence, and a set of distributions. And the idea is that you then replace by an estimate and basically monitor this for convergence to 0. So you monitor whether this converges to 0. You do it for various choices of the sequence bm, including bm equals m. And convergence to 0 suggests that in general your procedure is well calibrated in the sense that your estimates behave like true var numbers. So this is another idea of model checking based on the calibration function. What I want to do now is talk about how you might get a calibration function for expected shortfall. So let's go on to expected shortfall. So obviously what you want to do is you want to look for a function h such that you have this behavior. The expected value of some function of the expected shortfall at time t, and the loss given information up to time t is 0. And hopefully for a large class of distributions. However, you can't do that. There is no calibration function that will do this, and this is related to the elicitability that we will come to. You're not going to find such a calibration function. So all of the back tests that I have seen, and indeed the one that I proposed with Rüdiger-Frey, actually rely on calibration functions which are three-place, which reference the value at risk, the expected shortfall, and the loss. And the Acerbi-Seike tests, basically they introduce a couple of calibration functions, or one new one and one old one. So we look for functions h which satisfy this, and effectively the tests we derive are not pure tests of expected shortfall. It can't be tested in isolation. They are tests jointly of var and expected shortfall. The first calibration function, from the definition of expected shortfall, you have this identity. The loss minus the expected shortfall multiplied by the indicator of quantile exceedance. This has conditional expectation 0. So this immediately tells you that you could take the calibration function L minus E and the indicator that L is bigger than Q. Now I have normalized by dividing by E. That has some advantages that you will see, but I've taken this calibration function. And so for later purposes, I'll define what I call a K residual. So the K residual is this function H1 of var at time t, expected shortfall at time t, and the loss. Okay? Now, with Rüdiger-Frey, we looked at this idea. In fact, we called these things violation residuals. Basically, it's the amount of the discrepancy between the loss and the expected shortfall in the event that the var is exceeded. And we called these things violation residuals. And you obviously have the property here that the conditional expectation, or indeed the expectation, is 0. And so this is one calibration function. In Acerbi's paper, they give a second calibration function. So if you take this one step further, if you multiply it out and then get rid of the conditional expectation, or the conditional expectation here, this is another identity. This is another identity which is true and which gives you another possible calibration function of this form here. And so I've called this one H.
I is the indicator that you
Yeah.
bar.
Yeah. I is the, yeah, it's not, yeah. What is unfortunate here is that the I in this LaTeX and the L look exactly the same, but I is an indicator. Yeah. This is what Beamer class decided to do, but yeah, that's an I and that's an L. You could be forgiven for assuming that that was exactly the same thing. So the indicator that L is bigger than Q divided by E minus 1 minus alpha, and you get another calibration function. So this is true. I've used a slightly different scaling to Acerbi and Seike, because if you do this, then you get this little identity here. The second kind of residual is equal to the first kind of residual. So the S residuals equal the K residuals plus the indicator of violation minus 1 minus alpha. Okay, so this is basically the part that is used to test for violations. This is the indicator of a violation minus the expected value of that indicator. And K and S are two quantities that have been proposed for testing expected shortfall jointly with the VAR. But let's talk about these violation residuals. The most that you can say at this point in time is that these processes, if we regard them as processes, are martingale difference processes. They're FT adapted, and they satisfy the property that the conditional expectation is 0. But unlike the series that we used to examine value at risk, which was an IID series, we can't say anything stronger about these residual processes for expected shortfall, at least not without making stronger assumptions about the underlying model. So if, for example, you had what some people call the IID innovations model, so if you had a situation where the actual losses were generated in this way, that there was a volatility which depended on the past, but that volatility was multiplied by a completely independent and identically distributed innovation at every time point. So this is a model where sigma is the conditional standard deviation of the loss. ZT forms strict white noise, so it's IID. Let's say means 0 variance 1. So when you have this kind of structure, then you could then under this assumption, KT and ST would be IID processes. IID means 0 processes. But this is a strong assumption. Incidentally, the Garch model is in here, but also some non-stationary models. I haven't said here whether sigma t is a stationary process of volatilities. It could be a non-stationary process, but I have said that ZT is a stationary and independent noise. But in general, let's go back to this statement. You can't say an awful lot about these processes except they're martingale differences, and they have this property that the expected value given the past is 0. These are the processes for a Garch process. So this is the K process and the S process. It's the same one as before. Violations occur at the red dots, and you get the K process of residuals here. So if there is no residual, we just return a 0. And if there is no violation, you get 0. If there is a violation, you get these amounts which are shown by the red dots. This is the S process. If there is no violation, you get a bar of probability at the value 1 minus alpha, and minus 1 minus alpha, minus 1 minus alpha, and if there is a violation, you get these amounts here. In the case that there is a violation, the mean should lie where there's a red line and a blue line here, but they're on top of each other. The red line is where the mean should lie, according to theory, of the values where there is a violation. And the blue lines, which are basically superimposed on red lines, the blue lines are the actual empirical averages. Okay, so the point is that our tests are all our tests are based on whether these things are mean 0, whether we actually get mean 0 behavior when we estimate these or not. So actually formulating tests, you replace the risk measures by estimates. So you put the estimates in, and you consider testing for mean 0 behavior. Now, as I've pointed out before, there's a strong relationship between the S residuals and the K residuals, and indeed the calibration function that's used for value at risk. So in some sense, a test for the mean zero behavior of the S residuals can be thought of as combining a test of the mean zero behavior of the K residuals and a test for correct var estimation. But both of these residuals reference value at risk and expected shortfall. Neither of them can test expected shortfall.
Can you recall what K was? K?
Yeah. So K is given in this way, with this function here.
So it's the magnitude of the...
Yeah, it's the magnitude of the discrepancy between the loss and the expected shortfall relative to the expected shortfall multiplied by the indicator of a var violation. And so that's what it looks like. And you get plus minus plus minus. Here when you have a violation, you get a plus value. And when you don't have a violation, you get a very small minus value. But this process does have the property that the mean is at 0. The mean of the values which are above 0 is at this value here. So we have this link. And so let's think about testing K first. So testing the K residuals. So the null hypothesis here will be that the tail model is correct. The null hypothesis is a correct tail model beyond the alpha var. I mean, one could formulate the null hypothesis as being that we correctly estimate var and we correctly estimate expected shortfall. But I tend to think the aim is not simply to estimate two numbers correctly, but you're doing this because you want to validate that you have a reasonable tail model. So let us formulate the null hypothesis as having a reasonable tail model, or a correct tail model, beyond the alpha var. And the alternative is that these K residuals are systematically larger than 0. Because this null hypothesis implies that both var and ES are correctly estimated, and therefore that the expected value of the K residuals is 0. And the alternative is that the expected value is larger than 0. However, the alternative can arise from different deficiencies of the model. One way it can arise, if var is correctly estimated but expected shortfall is underestimated, then we can get this happening. But we may be misestimating both var and expected shortfall. This is a little bit the problem, that our test of expected shortfall is bound up in a test of var as well. We can't separate them. So probably the best way of using this test is to first test for var, and then if you're satisfied that var is reasonably estimated, you use the K residuals to test for expected shortfall. With the K residuals, saying that the expected value is 0 is equivalent to saying that the expected value in the event of var violation is 0. We can just concentrate on the points at which var is violated. And so we get there are various ways of doing it. When I wrote a paper with Rüdiger Frey, we said you could do a bootstrap test. You don't want to assume too much about the distribution of these things, so you do a one-sample bootstrap test. That's a reference to where you can find a description of the test. You get much the same results if you just do a one-sample t-test, it turns out. But of course, if you do a t-test, you make stronger assumptions. Here's an example. So suppose the true data generating mechanism, I'll tell you what it is. It's a gauge model of first order, 1-1. It has student innovations, so it's got heavy-tailed innovations, a certain degree of freedom. It's always estimated using 1,000 data. It could be 500, but it's 1,000 here. And it's re-estimated every 10 steps. So it's not re-estimated every step, but just every 10 steps. And the first forecaster uses model A. He uses the wrong dynamics, and he uses the wrong innovation distribution. The second forecaster uses the right dynamics, but uses the wrong innovation distribution. And the third forecaster actually guesses the correct model, but of course he is estimating the model, so he doesn't know the parameters. So the A and B are misspecified, C is correctly specified, and in all cases there is estimation error. And the aim is to estimate the 97.5% var and expected shortfall. Well, the interesting thing is that the simple binomial test, all of these models pass it. So this is a case where, on the basis of the binomial test, the p-values are not significant. So these models can fool the simple VAR test at the 97.5% level, but the two misspecified models fail the shortfall test and they pass the VAR test. So here's one misspecified model. Here's the actual violations you get. You plot out these empirical case statistics. The mean of these non-zero ones should be at 0, but the blue line is the actual mean and the red line is where it should be. So you see the systematic overestimation. Similarly for the S statistic, the red line is where the mean should be and the blue line is where it actually is with a misspecified model. But with a properly specified model, then these things come into line and the test is passed, or at least it's not failed. Okay, the Acerbi-Seike test. What happens here, this is a Monte Carlo hypothesis test. And if you want a reference for this, this is basically an implementation, although it doesn't say this, but a good example of where this kind of test is written up is the book on Bootstrap by Anthony Davison. And Acerbi and Seike, they apply it to both sets of residuals, but basically this is the situation. Again, we're testing for the correctness of the tail model at all time points against the alternative that we're using a model that tends to give us too large values for the S residual. And what you do in a Monte Carlo test is you sample losses under the null hypothesis. So we observe a particular value, which I'll call S0, which is an average of these S residuals. We observe that, but what we do is we randomly generate a sample from the distribution of S nil, S0, under the null hypothesis. We assume the null hypothesis is true, and we generate a sample from this distribution. So basically, I won't go through this, but you're basically just generating losses from the model, computing for every Monte Carlo replicate a value for the, call it the S statistic, and then you're comparing the Monte Carlo replicates with the one you actually have. And what is nice about this, and where I concur with Acerbi and Seike, in fact, you don't have to assume an awful lot to do this. You don't have to assume that these residuals are identically distributed, which I did implicitly in my bootstrap test of the K residuals, or a t-test of the K residuals. Implicitly, you're assuming that they come from a common distribution. Whereas here, there's absolutely nothing in the test which assumes identical distribution of these S residuals over time. It has the disadvantage that you have to record details of the models you use at each time point in order to resample. But this is what happens. Model B, this is for the K statistic, this is for the S statistic. You resample some Monte Carlo values, but this was the one you actually had, so obviously this doesn't belong to this distribution. So you reject the null with a p-value of 0. Here, much the same thing. Okay, the red line is slightly more interior to the distribution, but you still reject it with a p-value of 0. The B model was misspecified, but the C model is correctly specified, and you find that your actual value is embedded somewhere in the interior of the distribution. So
what quantile level are you testing?
So the p-value is with, so this is a p-value. So this is the probability that you would see.
Yeah, but you're testing an expected shortfall at a certain level. What's that level?
Oh, sorry, 97.5. 97.5 in all of
I
these.
went to levels which people use, like 99. It will be much less clean, right?
Yeah. Well, there'd be less. I don't know. Less violations, less of these things. I think it would still work at 90. I mean, I've done it at 99. It still works at 99. I don't really know why I picked 97.5, except that was in Acerbi and Seike. So
puzzle says 97.5
for expected shortfall. Okay. What has this got to do with elicitability? So that's the final little section. So there's lots of literature about this elicitability concept. Gneiting kind of threw the cat among the pigeons by suggesting that it means that expected shortfall can't be back-tested. And I'll come to that in my conclusion. But a non-formal treatment of this, so the key concept is the scoring function. So you have a scoring function S which measures the discrepancy between a forecast and a realized loss. And the forecast could be something like a VAR, and the realized loss is what happens. Forecasts are made by applying real-valued statistical functionals, such as mean, median, or other quantile, to the distribution of the loss. So the forecast is made by applying some functional to the loss, and this T could be the generalized inverse as a functional, or it could be the mean as a functional. And so suppose that for some class of loss distributions and some functional T, this functional basically solves a minimization problem. So this functional is the y argument minimizing the integral of the score over the distribution of the loss. Or if you like, the y argument minimizing the expected score, where L is the random variable representing the loss. L is a loss with distribution function FL, and Y is the forecast. Moreover, let's assume that TFL is the unique minimizing value. To keep this simple, then if TFL has this property of being a minimizer, well, firstly we say the scoring function is strictly consistent for T, and secondly we say the functional is elicible. So it appears as a minimizer. Now, what does this have to do with calibration functions? If you solve this let's suppose you can solve this minimization by differentiation and setting it equal to 0. So if you solve this minimization in that way, take the derivative and set it equal to 0. So this is solved at this functional. So basically we're saying that the expected value of H TFL is 0, where H is the derivative of the score. So what this says is you get these calibration functions popping up as the derivatives of score functions in the elicitability theory. Okay. So elicitability theory also indicates how we may derive calibration functions for hypothesis tests involving TFL. Now, the fact that we can't find a calibration function for expected shortfall is related to the fact that we can't find a strictly consistent scoring function for expected shortfall, i.e. expected shortfall isn't an elicitable risk measure. To give a summary of the main cases, VAR is elicitable. VAR is this functional, the inverse. This is the strictly consistent scoring function, or one of them. It's not unique. And if you take the derivative of this scoring function with respect to y, you get the calibration function that we use for the VAR tests. There's something called an alpha expectile, which is a risk measure that is defined as a minimum. So it minimizes a score function and is therefore elicitable by definition. But I won't talk about backtesting that. In papers by Bellini and Bignozzi and Siegel, they show that a risk measure is coherent and elicitable if and only if it's the alpha expectile. And this has a longer history, and work by Stefan Weber from 2006 also actually contains this result implicitly. I think, is that? Explicit, okay, explicit.
He does not use the word.
Yeah, okay, yeah.
Also, it's not limited to the coherent case.
Right, and it goes...
In that case, you get under elicitability the class of utility-based shortfall risk measure.
Yes, so, okay, so some references about that. Anyway, the upshot, expected shortfall isn't elicitable. No strictly consistent scoring function, no natural calibration function. So what about in the backtesting context? So var alpha t will minimize this conditional expectation of a score. Now S alpha q is the consistent scoring function for the quantile. This is it here. Okay, it has the property that its derivative is the calibration function for a quantile. Oops. And so that's what I mean by S alpha q. It's the scoring function for the quantile. You can actually compute these, if you like, theoretical var scores for the gauge process. I'll draw a little picture. For the gauge process, you can work out what form they take, basically the volatility times the score for the innovations, and you can work out what the average will converge to. I merely say that because I've drawn the scores for the same gauge process that I keep producing. So these are the violations. The var scores are these vertical lines, and there's a blue line here, actually superimposed on a red line. That means they're both on top of each other, and just so you can see that it's not at zero, this is the log scale. So the blue line is the mean var score, and it's superimposed on a red line, which is the true theoretical value for a gauge process. Now, just how would you use it? I realize I'm just running over, but this is sort of the punchline. So, elicitability for model comparison. The obvious thing, or the most natural use of the var score is model comparison. So assume you replace var by an estimate and you compute the var scores. You can use these to address questions of both relative and absolute model fit. The relative is perhaps more obvious. You compute this statistic for different models. So if you have two models that deliver two different sets of estimates, for example, my A model and my B model, or my B model and my C model, compute the estimates, compute these scores, you expect the better model to give estimates which are closer to the true var more often, so you expect that the average var score will be smaller. It doesn't, in reality, of course, it doesn't always happen that the superior model gives a lower average var score than the inferior model. But if you have enough data and the backtest is long enough, it will tend to indicate the better model. So that's model comparison, but you can also use it for model validation, I realized. I realized that you could extend the Acerbi-Seike idea for model validation. So you can also address the question of whether a score indicates that any particular model is good enough. So suppose you want to test the hypothesis that you're working with the right model. So this is a much more carefully defined hypothesis, or a much more fully defined hypothesis, actually a much stronger hypothesis than any of my previous hypotheses. I'm now assuming under the null that the model I'm using is the right one, and under the alternative, that is that the model I'm using is the wrong one. The right one at all time points, and the wrong one at least at some time points. So the model is fully specified under the null, and you can do the Monte Carlo test. That is, you can simulate losses under the null, and you can compute the var scores for the simulated losses and compare them with the var score for the actual losses. So you can do something like a Acerbi-Seike, but this time it's a Monte Carlo goodness of fit test based on the idea of minimizing the var score rather than a Monte Carlo hypothesis test. So if you do it for models A, B, and C, that's what you get for the misspecified model A and the misspecified model B, and for the model C, which happens to be the right model, but with estimation error, you get at least that your observed var score is within the distribution of var scores simulated under the null hypothesis. So that's one way you can use the var score for model validation. But let me conclude on where I've come to with this. So I've just got two slides. One is conclusions about backtesting expected shortfall, and the other is conclusions about elicitability. Backtesting expected shortfall. Value at risk has special properties that make it particularly natural to backtest. And namely, this is the fact that you get a Bernoulli trials process for the violation process for any reasonable underlying model. You can test the Bernoulli-Trials process behavior. The lack of a natural calibration function for expected shortfall, which is a consequence of the lack of elicitability, means that you can't backtest it in isolation. A backtest of expected shortfall is bound up in a backtest of VAR. It's feasible to develop joint backtests, and I've showed some of them, and Acerbi and Seike have shown some of them. They can detect deficiencies of tail models that are not detected by backtests of VAR. You can do very simple tests, such as the bootstrap test and the t-test, or you can try this Monte Carlo test of Acerbi-Seike, which doesn't make strong assumptions but requires very extensive storage of data in order to do the Monte Carlo replication. And we should be aware that ES estimation procedures lack robustness, so I'm just kind of neglecting that particular issue. The use of elicitability theory. Average VAR scores are very naturally used as comparative measures to distinguish between inferior and superior models. They're not infallible, but over time, these VAR scores will tell you which models are better than others for estimating VAR. You can also use an average VAR score as the basis of a Monte Carlo goodness of fit test, as I've suggested. Joint tests based on VAR scores at different levels would be a good alternative to joint tests of VAR and expected shortfall. I think if you're going to jointly test VAR and expected shortfall, why not just test VARs at two different levels? So the 95% VAR and then the median of the distribution of the loss above the 95% VAR, which is another VAR, for example. But there's one nice thing about the VAR score idea that distinguishes it from other metrics, and that's this. If as a forecaster you genuinely want to minimize a VAR score, then you are impelled to do the best possible job of estimating the conditional loss distribution. That is the optimal way to act if you genuinely want to minimize a VAR score. If in fact you were going to be penalized with a penalty that was based on the VAR score, then it would be optimal to estimate the conditional quantile as accurately as possible. You would be coerced into the right form of behavior. And this relates, in fact, to very early papers on the elicitability concept. Well, Osband's PhD thesis and then a paper he wrote with Reichelstein, suggesting that the great advantage of elicitability is it forces you to tell the truth. It elicits the telling of the truth, and it has this unique property. And so this is a sort of interesting but highly impractical idea that but it does beg the question, if you're going to do that, do you really want a bank to estimate the conditional quantile of its loss distribution for the trading book as accurately as possible, or is that just a means to another end? If you wanted to do that as accurately as possible, then in fact the VAR score incentivizes you to do so. Okay, I think I started 5 minutes late, but I've ended 10 minutes late. So
what is the scoring function again for the VAR?
What is the scoring function?
Just the...
what does it look like? Yeah, it looks like that one. It's the absolute difference between the loss and the forecast. The indicator that the loss, okay, you can do it either way. This, I've put it, the indicator that the loss is less than the forecast minus alpha.
It's one of them.
Yeah.
You have a whole class.
Yeah, there's a whole class, and I don't know if...
Yeah, so when you say penalty proportional to the scoring function, what do you mean? You mean...
Okay, so you as a bank are going to submit your okay, the penalty proportional to the scoring function, that the financial penalty you pay is given by this.
But that's for one observation.
That's for one.
Your sample, you average on the sample, is that what you mean?
Okay, good question. Average over the sample. You could pay this every day, and I think you should pay this every day into a fund.
But that's the case, right? Because if you if your loss exceeds your VAR, so suppose you provision for capital based on VAR, and if your loss exceeds your VAR, you will increase. You'll have to put.
I'm not sure it's quite as reactive as that, because you have this kind of 60-day averaging process to get the regulatory capital. I don't think it's quite as reactive as the idea that every day you pay into a fund proportional to whatever this score is.
Yeah, but so let's say the reaction time is 60 days, but it's based on the scoring function.
Yeah, though I think the optimization problem the bank does is kind of diluted by other considerations. So if it really just wanted to minimize the amount of money that it was paying into the VAR penalty pot, then it would have to do the best statistical job. But it's probably doing some sort of, suppose it was doing that, but at the same time it was wanting to keep its VAR numbers relatively.
You're thinking about banks, but there's another case where this concept is used a lot. That's margin requirements.
Right, okay.
Margin requirements is the exchange charges you a margin on your portfolio, which is recomputed every day, just like this. And it's typically VAR or expected shortfall, depending on which exchange, which instrument. And if your loss on a given day exceeds your margin, immediately you have to replenish the next day. So because the exchange doesn't want to pay for you, so if not enough money, you have to replenish.
So this is more like a collateral, or
yes,
sounds more like collateral.
But margin is collateral.
Yeah, in that sense. So
Okay, so if you don't want to, if you want to replenish minimally, you should be incentivized to estimate as accurately as possible, if it really is quantile based.
But you don't estimate it, the exchange does.
Okay.
So if they don't charge you enough, they will lose the money if you disappear. So it's done in this way every day.
Okay, but it is an interesting idea that how to set things up to elicit the telling of the truth, and that's what interested Osband in his PhD thesis, getting contractors to actually give truthful estimates of costs. Once you've decided what you want them to tell the truth about, if indeed you do want them to tell the truth about, you know, their best view of the conditional quantile of the loss distribution for the trading book, of course, ultimately that's a means to an end of being.
But I have a question about your example, because in your examples you typically had many values below the threshold, and then you have some spikes going way above. So, and it passes the test in your examples because the average is around the expected.
Yeah.
But so I don't really understand why this is a good outcome, because if the goal is to provision for the loss, expected shortfall viewed in this way, and is you're averaging the loss across different outcomes, as if you could compensate the shortfall on a given day with an excess on another day. But this is certainly not the case. You cannot transport collateral or capital from one period to another. So whereas in the VAR, the interpretation of VAR as a worst case loss in a set of scenarios, that I think for me that's what makes it attractive, because you say, well, okay, I don't charge you the loss in all scenarios because this would be infinite, but I take a set of scenarios, and in these scenarios you should have enough to cover your loss. So it's a worst case.
Well, it's a 99% or 97.5% worse. These are all these are the 2.5% of cases.
Yeah, but you see, the result in Basel has been the following. They say, okay, expected shortfall for the same level of quantile is more severe than VAR. It's always bigger.
Yeah.
So if we ask these guys to move to expected shortfall from 99%, well, they won't like that. So because we move to expected shortfall, we feel more, we feel that we're being more severe in the assessment of risk. So we
So
lower the quantile
Yeah.
simultaneously. This is the story behind 97.5, because if you calibrate it for
Yes.
whatever distribution it is, I don't know, it's a Gaussian.
That it doesn't make a big difference to the overall
But
capital
it's-
requirement.
But this means that you
Calibrating the
now
result.
You lose.
you have more violations in the tail cases, because
Yes.
when you estimated you're averaging, this means in your head you're compensating the loss of something else with the gain in other scenarios. But this compensation isn't real. It doesn't materialize. So in practice, you will have more shortfall in those extreme scenarios.
Yes. I mean, that observation is true, but
For me,
Yeah.
that's the problem. It's not the elicitability problem.
mhm.
You correctly point out it's not the.
Yes. And the idea of doing a var and a median var is possibly interesting, but yeah. I don't know. I mean, on the other hand, it's useful to have a way of, so you can get var right by accident in a sense. You can get var right by accident even with a fairly crude model, but the idea of probing a bit more deeply to work out if the bank has a reasonable understanding of the full tail of its loss distribution is possibly worthwhile. So when you look at secondary risk measures like expected shortfall or like a median VAR above the VAR,
Another var.
pardon?
Another
Another VAR, then you probe a bit more deeply into the tail and you gain a bit more satisfaction that they've got a reasonable understanding of the tail and they're not just lucky that they can sort of get a crude handle on the 99th percentile. So you do, for example, here find cases where the VAR tests are passed, but you look at this joint test of the VAR and the expected shortfall with these residuals and you see the glaring deficiency of the tail model they're using. That I believe. Okay, yeah.